Hi, I'm here to present my course project for 591. It's about the RF pulse design for the fat separation. The personal goals for me is that I want to understand the SOR pulse design method. I also want to understand two fat separation pulse, the fat stat pulse and the spectral spatial pulse, about how they work. The project goals, it's first I want to explore the feasibility to apply the FAT-SAT pulse at the low field. Based on that, I want to design the effective FAT-SAT pulse and spectral spatial water excitation pulse at the 0.5 Tesla. So FAT-SAT techniques it's being widely developed in different applications for different body parts. So there are two purposes. The first one is to use FAT-SAT pulse to reduce the chemical shift, and also when we apply the FAT-SAT pulse combined with other pulses, it usually gives us a higher image contrast for better visualization of the tissue and or the lesion part of the body. Talking about the water and fat chemical shift, the water and fat chemical shift they always has the 3.5 parts per million in different B0 field. But it's also worth to mention that we set the mean fat peak. It has exactly off resonance frequency, but the fat set has many different components which gives a wider range. So when we apply the chemical shift based fat saturation problem techniques, we can only guarantee that at most maybe 90% of the fat components can be saturated. But in lower field, the frequency offset between the water and fat is much more smaller. It's at 0.5 Tesla, it's about 74 Hertz, which require us to develop the B1 profile, which has a much narrower bandwidth. So the ideal case is that we have infinite long B1 pulse, which can produce exactly perfect square, but we cannot achieve that. So in order to find a reasonable pulse duration, we need to compensate the trade-off between the shape of the slice profile and the B1 pulse duration. For the fat-SAT pulse, it generally gives us 90-degree non-selective pulses followed by a spiraling gradient on the transition plane, which only leaves the water magnetization remains. But for the spectral spatial pulse, the key part is that we modulated the gradient and the B1 envelope at the same times to excite it on the spatial domain and along with the spectral domain. So here are three main relationships. So the envelope of the B1 determines the frequency profile on the spectral domain, and the period of the sub-pulses determines the spatial domains, which is the slack thickness, about how it can perform. And the spacing between each sub-pulses directly determines the spacing of the slice profile of each sub-pulses, which is also very useful and important. So in order to design a good B1 pulse with a good performance, I use the SLR RF pulse design tools to get the B1 profile, and then I use the block simulation to generate the slice performance at both cases with considering the T1 relaxation. So very similar to the FIR pulse design, I here define the normalized transition bandwidth and the saturation efficiency to kind of evaluate the pulse performance I designed. So here, the first questions I want to answer is that in how short the pulse duration I can achieve at different cases. So at 3 Tesla, I think the shortest we can achieve when we have the time bandwidth product at 2, and we can achieve around 4 milliseconds. But for 0.5 Tesla, we have much longer duration, which is around 25 milliseconds. But after I plotted those two cases of the slice profile, I think both of their transition band is much more longer than what we desired. So we need to compensate and to find more reasonable pulse duration with trade-off between their transition band. So here I plotted the two mean parameters I wanna find a trade-off between. So we wanna achieve the both parameters as shorter as possible. So in both cases, I think the maximum phase and minimum phase, but they all have a better performance for than the linear phase case. So I also assume that 50% of the transition bandwidth should be good enough. So to achieve that, I think compensate for the pulse duration around 7 milliseconds at 3 Tesla and around 35 milliseconds at lower field should be good enough. With the considering the T1 relaxation part in real case, I think when I found the pulse duration of the to evaluate their saturation efficiency, I think in higher cases they can both achieve around above 95% of the saturation efficiency. At low field, I think if we choose the minimum phase case, it's very robust to the pulse duration, and it can achieve about 94% of the efficiency saturation. So based on the both I illustrated, I think I choose the very reasonable parameters in both 3 Tesla case and 0.5 Tesla case, which both use the minimum phase, and they have the desired bandwidth with a reasonable transition bandwidth. I plotted the B1 and the frequency profile. So for the spatial pulse, I choose the longer B1 duration because I think it's very important to separate the sub-pulses slice profile to make sure that they have a narrower bandwidth. But it's also important to separate the spacing of each sub-pulses slice profile, but this will often requires a higher performance of the gradient in higher field case. But we don't need to worry about in the lower field case, because the spacing between each slice profile sub-pulses it's much more narrower, and this allows us to have a kind of longer sub-pulses duration and their spacing, and with regarding to the much lower gradient performance. But one thing is that we also need much longer time duration, which is about 40 milliseconds. So the conclusion is that I designed the two pulses for fat saturation using the fat set pulse and the spatial pulse, and in lower field they can achieve around 33 milliseconds and 40 milliseconds correspondingly. So in both cases, in different fields, I think those the two fat saturation pulse they have different properties, and they have their potential to being applied to the low field. And the challenge I identified there is that first I had a problem to differentiate the spectral frequency and spatial frequency, and also I found it hard to manually find the optimal solution when you have a problem with many trade-offs. And the lessons I learned is that sampling theorem is very important, and I also learned a very good and efficient way to illustrate it a bit more complicated problem. Thanks for listening. That's all I have.